Okay, and then I'm going to visit one more topic quickly from the first week. So I talked about something called bond duration, and it turned out that was just a linear approximation. So I was using the derivative to make a linear approximation of a yield curve for a bond. So this is the yield curve for a bond. The price formula, so the price of a bond is it's just the discounted value of the future stream. So what I'm going to get paid is the face value of the bond in n periods. And then the sort of my reward for giving somebody money now that they're going to pay me back in the future is they're going to make coupon payments every month. And so this actually should have had parentheses around it. And so what I'm after here is just the discounted value of this stream of coupon payments plus the discounted value of the face value that I'm going to get back when the bond matures. So I have coupon payment, number of periods remaining. So n is just how many more periods I have to wait before I get my money back. F is the face value, so that's what I get. That's sort of, usually it's how much I've sold the bond for, and then I just get my money back, but at some time in the future. And then lambda, you can think of this as the interest rate, but it's for a bond, it's called yield to maturity. And so last time I said we can make a linear approximation. So I introduced this concept called duration, but then I showed that it was basically just a simple transformation of the first derivative, and so I could use that to make a linear approximation to my bond. And so if I did that at the point 10% and 100, then you can see, maybe between 8% and 12%, the linear approximation is pretty good. But if you deviate a long way from there, then the distance between the actual price and the approximation gets pretty big. And I said we could improve this by adding a quadratic term. And so we'll see that that quadratic term is just a degree 2 Taylor polynomial. So the quadratic term is called convexity. And we just have to compute it by looking at the present value of the future stream of payments. So if I say AK is the amount that I'm going to receive after in the kth period, then I want to find the present value of that amount just by discounting it by a factor that's equal to 1 plus the yield to maturity. And then I'll say that the current price of the bond is just equal to the sum of the present values of all of the future payments I'll receive. And that's equal to the sum of all of these amounts discounted by 1 plus lambda. Then the term convexity is defined to be 1 over p times the second derivative of this price formula with respect to lambda. And so I said the price was equal to this thing over here. And so I'm going to just put 1 over p times the price. And instead of having this in the denominator, I just think I make fewer mistakes when I can use the power rule. So I write that as 1 minus lambda to the minus k instead. And then the only thing that has a lambda in it is this term here. So I'm going to move my derivative operator across the 1 over p and then across the sum. So we have this linearity property, remember. So the derivative of a sum is the sum of the derivatives. And then in one step, I will take two derivatives. So I had this to the minus k. So I'll get k here, and then a k plus 1. And since I'm doing it twice, the minus signs are going to cancel each other out. And then I end up with minus k plus 2 in the denominator. So the denominator, the power is getting smaller. And you can write this as 1 over p. So I'm going to take this plus 2 here and write it as 1 over p times the quantity 1 plus lambda squared. And then I have inside the sum k times k plus 1 times these a sub k divided, so the discounted future payments again, essentially. And now I need a point where I can make my approximation. So I already saw that in my graph it was the point 10% and 100. So that gives me a lambda naught and a p0. So this is some point where I've actually evaluated the price of the bond. Then I have dm is something called the modified duration, and c is the convexity that we calculated on the last slide. And so if you look in the investment science textbook, you'll find that just the change in price of the bond is approximately equal to minus the modified duration times the price times the change in the interest rate plus 1/2 times the price times the convexity times the change in the interest rate squared. And so let's just try and write this out into things that look more familiar with what we've just done. So I'll say delta p, that's just going to be the difference between p and p0. So I'll leave the p on the left-hand side here, but I'll move the p0 to the right-hand side. So I have p0 minus the modified duration times the price times lambda minus lambda 0. So that's delta lambda. I'm just going to think of that as lambda minus lambda 0. And then 1/2 price times convexity times lambda minus lambda 0 squared. And then if I go back and substitute in how we got these terms in the first place, the modified duration times price and price times convexity, both of those just came from the derivatives of this price formula for the bond with respect to lambda. So the first one is just dp d lambda evaluated at p naught. And then price times convexity, that's the same thing as the second derivative of p with respect to lambda evaluated at p naught. So really all we've done when we use modified duration and convexity to approximate the price of a bond, we've used a order 2 Taylor polynomial to approximate the same thing. And so just to finish up, this is the picture of what that looks like. So the blue curve is the actual price curve, yield curve of the bond. And the dashed black line is the linear approximation. And then the red line is the order 2 approximation. And so again, in maybe a little bit wider now, maybe 6 or 7 to about 13 or 14, we have a pretty good approximation. But then as we get into more extreme values, much further away from the point we used to build the approximation, the true yield curve is deviating from our approximation. And so on this side, it's higher than the approximation, and on this side, it's lower.